All right, so what we're looking at here, we're back to section or chapter 16 after looking at second and third derivatives here. What we're looking at here is particularly the second derivative. When we're talking about concavity, we're dealing with, or we're looking at the second derivative. Okay? Now, you'll see here a little picture. We say something is concave downwards when it looks like this, and we say it's concave upwards when it looks like this. The challenge, probably the biggest challenge here, is if you have that concave downwards and the concave upwards on the same graph, how do we know where it stops being concave downward and starts being concave upward? Looking at the values of the second derivative, and particularly what we just saw on the homework problem, where that second derivative equals 0, is that right there. Okay? That's what we're going to be looking at as we move forward here, okay? But that's kind of the challenge, is finding where that is. Now, we said that the second derivative tells us about our acceleration, okay? Acceleration, the best example I can think of is if you think of an airplane kind of in a nosedive. You've probably all seen a movie where this happens somewhere, but you've got this plane that's falling and falling and falling and falling, and all of a sudden, you know, the pilot wakes up or whatever, and or they knock out the bad guy and they grab the stick, and they were speeding up because of gravity, because they're just in this free fall. But then the pilot grabs the stick and he starts to pull up. Okay? And that, at least, he doesn't actually start going up right away, does he? For a while, he just stops speeding up towards the ground. In other words, his acceleration is decreasing. He's not even moving up yet, he's just not moving down as fast. So here he's pulling up, here's where he grabs it. He's pulling up, and his acceleration is decreasing until finally his it starts to kick in, and it starts. He's able to pull out of the dive. Okay, so he might grab it here. Actually, I should say he might grab the stick here. He starts pulling up. He slows. His acceleration is decreasing, but then it hits 0 right there, and that's where the acceleration actually starts going in the right direction. Okay, and then it's able to speed him up fast enough to where it hits the minimum value, and now we're going into positive velocity. Okay. So that's kind of the idea here, is finding out where that 0 point is, where we stop accelerating downward and we start accelerating upward. Okay, that was this point right here between the aspects of concavity. All right, now let's look at a couple of things here. Remember, derivatives give a rate of change. We've talked about this a little bit. Okay, f prime of x is the rate of change of the position, which is velocity. And then f double prime is the rate of change of the velocity, which, like we said, is acceleration. Now, you can see here, on the concave downward curve, you'll notice the slope of these tangent lines can be positive, can be zero, can be negative. Alright, but as we go from left to right, what's happening to our slope?
Decreasing.
It's decreasing. Okay? F prime of x is decreasing. And notice not just in magnitude, like it's getting closer to zero. It's actually decreasing now into the negatives. Okay? So, f prime of x is going to be negative. Okay? And that's one of those things where, remember we did the sign diagram with our first derivative? We could do a sign diagram with our second derivative as well to find intervals where we are concave up or concave down. Okay? Now likewise, if the curve is concave upwards, notice what happens to the slopes of our tangent lines. It was -2, now -1, now 0, now 1, now 2. Our slopes are increasing, which means our second derivative is, what is it? Positive. Okay?
But aren't you kind of finding the same points as the sign diagram of the first one? Because we looked at if it goes up, like if it's positive or -2.
Well, except here's the thing. On the sign diagram for the first derivative, your interval would go from to the left up here to wherever this is. And that tells us where the slope is positive or the slope is negative. Here we're talking about where the acceleration is positive or negative. So that's where those points of inflection we mentioned are going to come into play.
It has odd Q after you're done.
Okay. So that's what we're looking for here. A point of inflection is a change in curvature. Okay, a change in curvature. A point of inflection is a point on a curve at which there's a change of curvature or shape. All right. So, for example, on this one on the left, from here to the left, we are concave down. All right. So f double prime of x is going to be negative. Okay. From here to the right, we are concave up. So f double prime of x is positive. Okay? It's positive. Okay? And then of course at the point of inflection, your f double prime of x equals 0. Okay? Now there is one thing I'll point out right here. We've seen this point before.
Oh, the plateau.
A plateau point. Okay? A plateau point is kind of a unique point in that it not only is a critical value, but it also is where the second derivative is 0. Okay? So both the first and second derivative is 0 here. So that's what's interesting. You don't have a change in increasing or decreasing, but you actually do have a change in concavity here. Okay? So if you're thinking about, on this side we are decreasing. Okay? But also on this side we are decreasing. Alright? That was our first derivative. Over on this side, however, we are concave up. Over on this side, we're concave down. Okay? So these plateau points are kind of interesting points. And that actually is something to keep tucked back in your memory. If you are trying to sketch one of these, and you already found a plateau point, you automatically know it's going to be one of the zeros of your second derivative, too.
But you still have to find, like, still do this process because there might be more, or?
Yeah, there might be more. Yeah.
So, even though that's concave up and then concave down, does this rule on the left side still apply where f double prime is positive during a concave up and then negative on the concave down?
Yes.
How, can you like go through maybe just x to the third, because I know x to the third is a plateau point like that, and just show us why that is, because I'm having trouble visualizing that.
Yeah. Sure, we can do that. Let's say f of x is x to the third, okay? You guys know that looks like this. Okay,
Well, let's make it negative x to the third, just so it's going the other way.
okay. Oh wait, that didn't help. Hang on, I should flip it.
Yeah, you can just.
There we go.
Yeah, I need to
Did it do it?
and then
It didn't do it.
I think you have to do
Evidently it doesn't like it.
just
It's
turn it
really
90 degrees.
I'm not sure what's going on.
Just make some refresh.
Yeah. Here we go. Got that. We got that. Okay. So f prime of x equals 3x squared. Okay.
Negative 3x squared.
Negative 3x squared, yeah, because we made that negative. Alright. So if you were to do a sign diagram, okay, your critical value is going to be, there's only going to be one, it's going to be at 0.
Yep.
But if you plug in a value to the left, you're going to get a negative. If you plug in a value to the right, you're going to get a negative. So, and as you can see here, here's our critical value. It's decreasing as we come at it from the left side, it's decreasing as we pass it on the right. Alright, so that is a plateau point. Okay. Then we have our f double prime, our second derivative, that's a negative 6x. So again, where that is 0 is going to be at 0, but as you go to the left, it's going to be negative, which means we're concave down. Or I'm sorry, no, it's
Yeah,
I
as
got
you
that
go
in
left, it
reverse.
actually is going to be positive.
I got that in reverse, sorry. On the right hand side it's going to be negative, so we're concave down. On the left hand side we're going to be positive, so it's concave up. Alright, so you'll notice here we're decreasing but not as much as we approach this point of inflection. We're decreasing, but it's slowing down. Until finally, at this moment right here, we're not increasing or decreasing. Our acceleration is 0 at that moment. Then, it starts speeding up downward, okay? It starts accelerating downward, which means we're concave down. The acceleration is negative, okay? And maybe that'll help too, is think of a positive acceleration means we're accelerating upward, like here. We're accelerating so it's not going as far down as it could, it's getting pushed up, you know.
Okay, that was the part I was having trouble visualizing, is how it would still be like a positive acceleration. Okay, that makes sense then.
Alright. So, that's kind of the basic there. You get your critical value, and you can tell increasing or decreasing. You get where the second derivative is 0, and you can tell whether it's concave up or down. And again, finding that point of inflection there tells you where the kind of the turning point is in the whole situation. Okay. This kind of gives us a little summary of both the first derivative, our turning points, or stationary points, which were also critical. Okay, remember stationary points is the same as a critical point. Okay, and then we have these points of inflection. Inflections are where the second derivative is 0, but then there are these ones, and the term there is a term for these plateau points that are, you know, plateau points and points of inflection. They're what are known as stationary inflections. Okay, and that's this area here. That's what we were just looking at. Okay.
And that's when it's a plateau point.
Yeah, these are plateau points. Okay. These are, well, I guess all of these technically are points of inflection. These ones, they call them non-stationary because these are stationary because it's a change in concavity, but also at that moment we're not increasing or decreasing. So it's stationary. These are non-stationary because it's a change in concavity while we're continuing to increase or decrease. Alright. So, let's try one all the way through here, okay? Let's find points of inflection and intervals of concavity for this function. Obviously, we could put this together with everything that we had done on the quiz. Alright, this would be like steps F and G or something like that, you know, in our process of sketching an entire curve. But we'll just do the new portion of it here. F prime of x with a polynomial, you guys are good at these now, so 4x cubed minus 12x squared. F double prime of x is 12x squared minus 24x. Alright? So, if we're going to find points of inflection, first of all we need to find out what values of x give us a second derivative equal to 0. Okay? Obviously we can factor out a 12x, you get x minus 2, so it's when x is 0 or 2. Okay. So that tells us what the actual points are. The points are 0, 5, right? Because that's just the y-intercept. In this case, the y-intercept is a point of inflection, 0, 5, and also the point 2, 16 minus 32 is negative 16 plus 5, that's a negative 11. Okay? So when we went to graph it, those would be 2 more points that we would hit on our graph. But also now we can tell a little bit about our graph by doing a sign diagram. Okay? And here it's for concavity.
Do these points of inflection also go on our sign diagram now that we've learned them? Like, should we also put them on?
Well, you're going to do different sign diagrams for the first derivative and for the second derivative.
Okay.
It's not like when you had those things that were eliminated from your domain, and you added that to your first derivative one. You're not going to add these to that same sign diagram. You're going to have a new one, and you're going to be testing the second derivative. So we're going to put 0 on here and 2 on here, and if we plug, let's say we plug a -1 into our second derivative, f double prime of -1, we'd get 12 plus 24, positive 36. So that's positive, which means we are concave up. Alright? Now if I try a value between 0 and 1, or 0 and 2, if I try 1,
Couldn't you just do it, like, just know it? Because if those have to be points of inflection, right? So if you've got the positive, then one of the next one automatically have to be negative, and the other one will be positive.
that is typically how it'll work. If you got like double roots in there somehow, or if you, or if there were asymptotes or some things like that, that could affect how things work. So it doesn't take a whole lot to try it, just to be safe. You know, if we tried 1, 12 minus 24 is a -12, so I know that that's negative, so this one's going to be concave down. And then if I try something to the right of 2, if I do f double prime of 3, I'm going to have 12 times 9 is 108 minus 24 times 3 is 72. 108 minus 72 is positive, which is all that matters. Okay, so this is concave up as well. Okay? So add this to what we've already been looking at with the curve sketching in the first derivative, and here you get more detail, you understand a little bit more about your curve as well. Alright? Alright, that'll be it for today. Have a good day.